Langmuir adsorption isotherm. Langmuir was able to give us the relationship between the absorbed gas molecule on the metal surface and the gas molecule that is left in the solution. So of course we know that a metal or an element is a substance that contains only one atom. So let's say we have a metal, say gold, which is made up of small atoms that they are arranged in a fixed position which they are equivalent. So an element is a substance that contains only one kind of atom. So this is gold. This is the atoms. This is the atom that make up gold. So since this is a metal, so it gives us a view that the gas molecule can be absorbed on each of these, and it's not as a function of maybe the site here is absorbed or not. It has equal right to be absorbed, to be absorbed by gas molecule, to be taken by gas molecule. So this can be absorbed first, this can be absorbed, but it's absorbed in such a way that one monolayer is formed. So this is let's say this is our ratio of gas absorbed, and this is the ratio and rate of the gas that are not absorbed. So it came out with, Langmuir came up with 4 or 5, let me say 5, I've gotten 5 here, 5 adsorption, which is gas molecule are absorbed on the metal surface in such a way that only one monolayer is formed. That is, one layer like this will be formed on the metal surface, because metal surfaces are made up of atoms which are fixed together. They are rigid metals, they are strong and they are rigid. So the intermolecular force is very hard. So each of these atoms rather can be absorbed only one gas molecule. And it's not a function as if whether this is absorbed or not first. Each of them has the ability to be absorbed at the same time, at the same rate. So another assumption that he made was that gaseous molecules behave ideally. That is, they follow partial pressure, law of partial pressures. No interaction between adsorbed molecules and non-absorbed molecules. That is, the absorbed molecule in the solution, and that is in the gaseous phase, and the one that is on the metal surface. So there's no interaction between them. All the sites on the surface of the metal are equivalent. So each of them has the right, each of the atom has the right to be absorbed. It's not a function as whether one is absorbed first or the other is to be absorbed. They're not in a queue or something. So an adsorbed molecule is fixed. So when a metal surface is being absorbed, it is fixed. The molecule will be fixed on it. Absorbed molecule is fixed. So it will be fixed on it. It will not move from one atom because the atoms are very close to pack together. So let's say the rate of absorption, and let's have a reaction. Let's say we are representing our gas molecule with A. When it reacts with, or when it's formed, when the molecule comes to on metal, following forward reaction to form AM, this is like intermediate, can go back again to form A plus M. So let's say this is our rate of adsorption, which is Ka, and this is our rate of desorption, Kd. This is represented by the rate constant Kd and Ka. So rate of absorption A is proportional to the partial pressure of gas A. This is our gaseous molecule, and this is the metal. So, and also rate of adsorption again also varies proportional to n to bracket 1 minus theta, where n is our number of sites present, and this is a fraction of the number of sites absorbed. So we can combine the two. R A very proportional to P A N into bracket 1 minus theta. So when we put our proportionality sign, when we remove our proportionality sign rather, we have rate RA to be equals to K A P A to bracket P A N to bracket 1 minus theta. So let me divide the terms here. RA, rate of absorption, Ka, rate constant for adsorption, Pa, partial pressure of the gas molecule, N equals to total number of sites. I say total number of equivalent sites present, theta, the fraction of sites absorbed, is same thing as number of sites adsorbed all over total number of sites, number of sites absorbed or occupied. It can be all occupied all over total number of sites. Let me say total number of sites present or available on the metal surface. So we know at equilibrium. So let's talk about rate of desorption now, which is the site that the gas does not absorb. Rate of desorption RD equals to or very proportional to N theta. I've explained what N means. N is number of sites present, this is fraction of sites absorbed, and this is rate of desorption. So rate of desorption, we remove our proportionality sign, we have rate of desorption. This subscript please RD, let me put it R small d equals to K of desorption N theta, and we know that at equilibrium forward reaction equals to backward reaction. I mean the rate of forward reaction equals to the rate of backward reaction. So we now have our RA to be equals to RD. Therefore we can say Ka Pa N into bracket 1 minus theta equals to Kd N theta. So we can divide both sides by Kd. We divide both sides by Kd. Divide both sides by this cancel out here. And we know our Ka over Kd equals to K capital letter K. Let me put E, K equilibrium. So it's our K equilibrium. So this can be represented as this. So we can substitute this here. So we have our K E P A N into bracket 1 minus theta equals to N theta. N is common to both sides, so we can cancel N out. So we have our K equilibrium P A 1 minus theta equals to theta. So we can open the bracket here. We have our K E P A, this multiplied by this, then this multiplied by theta will be minus K E P A theta equals to theta. So we can rearrange this equation, then we take this to the other side so that we have, now we factorize our theta out. So we have our K E P A equals to theta plus K E P A theta. So K equilibrium P A equals to theta into bracket 1 plus K equilibrium P A theta. No. So theta, we have factorized theta out here, sorry. So we can now divide both sides by this 1 plus K equilibrium. So we have our theta at the other side. K equilibrium PA equals to theta into bracket 1 plus K equilibrium PA, everything divided by 1 plus K equilibrium PA all over 1 plus KEPA. So this can cancel. So we have our theta to be equals to KEPA all over 1 plus KEPA. So when we plot theta against pressure, partial pressure, we get a graph that will look like this. So meaning it is increasing, the ratio is increasing with pressure. As you get to a point, it's balance up and remain constant. So at low pressure, because the gases are behaving ideally, so it follows partial pressure. So at low pressure, KEPA is very less than 1, so it is negligible from this equation here. So our theta can be equals to KEPA all over 1, which is the same thing as theta equals to KEPA. That means it follows at low pressure, it follows first order reaction. First order reaction will be first order. But at high pressure, where KEPA is much more greater than 1, that is, from here 1 is negligible, so theta equals to KEPA all over KEPA. So theta equals to 1. When I say it's negligible, that means you can remove it. As I'm removing 1, I'm removing KEPA. When I say it's negligible, it means you can remove it. It has no effect, so it's more or less that it is not there. That's why. So at very high pressure, KEPA is very high, and it's very, very much greater than 1. So theta equals to 1, meaning it follows a zero order reaction. So we have a raised to power 0, same thing as 1. So meaning it follows. So at high pressure, it follows zero order reaction from here. So that is Langmuir adsorption at the time. Thanks for watching.